Hi, welcome to today's lesson on temperature and heat. I saw that when people are mixing the definition of temperature and heat, but temperature and heat are quietly differ from each other. We know that temperature refers to how hot or cold of the body. Simply, temperature is the degree of hotness or coldness of a body. That means temperature is a fundamental quantity, that is a scalar physical quantity, in a thermal or heat phenomenon. Also, temperature is the measure of the average kinetic energy, because when the body gets energy or heat, the kinetic energy of that body is increasing. When we say degree is a fundamental unit of temperature. Let's say, if two objects or two bodies with different temperature, even though their mass is the same, one with 100 degrees Celsius and the other with 300 degrees Celsius are in contact, the temperature or the heat will flow from high temperature to low temperature until thermal equilibrium. We know that matter is made up of moving particles like molecules, atoms and ions. So in a solid, these particles are close together. That means it only vibrates. Whereas in a fluid, when we say fluid, liquids and a gas, the particles can move around more freely. So temperature and heat are quietly differ from each other. When we say heat is one form of energy. It is the form of energy. It's measured in joule. Heat is measured in joules. It is also a scalar physical quantity. It is the flow of energy from hotter to the colder body. Therefore, this heat flow is equal to the sum of kinetic energy and potential energy. The kinetic energy and potential energy gives us heat flows, or simply the heat. Assume we do have two bodies, let's say let's say we have two different beakers which have, look, this is 1 kilogram at 100 degrees Celsius, and this is 500 gram, which is 0.5 kilogram at 100 degrees Celsius. This is, let's say, beaker A, and this is beaker B and beaker A. Therefore, imagine two beakers of boiling water. Beaker A contains 1 kilogram of boiling water, and the beaker B contains 0.5 kilogram of boiling water. They are both at the same temperature, 100 degrees Celsius, but there are more particles in beaker A, and so there is more energy content, within it than beaker B. A more energy content than B. More particles move there and there. That means the energy it gain is high. When we heat up a substance, we are transferring energy to the substance. If you heat up the object, or when we heat up the object, we are transferring energy to that object. The particles of the substance gain kinetic energy and they move rapidly. That means their kinetic energy will be increased. The bond between the particles in the substance are broken, and the bond is broken. and the potential energy of the particles also increase. The potential energy increase. When this happens, the substance changes its state. Changes its state. Therefore, the temperature is directly proportional to the kinetic energy. That means the same particles with different temperature means which has the more energy or the more heat or temperature gains more energy than the other. Therefore, temperature, the speed, and because kinetic energy is depend on the speed of the body, which is 1 over 2 mv square. Therefore, when the temperature increases, the kinetic energy increase means the speed of the objects also increases. So let's see this using the diagram. Using the diagram. Assume, let's say we do have here the number of molecules versus speed. Let's say at 0 degrees Celsius, let's draw the different diagrams like this. Okay. Let's say this is 0 degrees Celsius, let's say 100 degrees Celsius, and 2000, let's say 2000 degrees Celsius. That means they are in different temperature, in different time. If we are looking up the figure, we can see that at 0 degrees Celsius, most particles have relatively low speed. Look, the speed is around this, relatively low speed. Hence, a relatively low kinetic energy. At this, kinetic energy is what? It is low. Why? It has no speed. Therefore, only relatively small number of particles have high speed and high kinetic energy. As a substance is heated up to the high temperature, for example 1000, let's say this 1000 or let's say 2000, the graph shows us the average speed and consequently the average kinetic energy of the particle is greater than that of 0 degrees Celsius. Therefore, at this point the kinetic energy is increased. Why? The temperature is increased means the kinetic energy also increase. Therefore, when the temperature increases, the particles inside the solid can be vibrate mostly, or in the liquid they can flow, or they get high kinetic energy. That means they get the high speeds. Therefore, let's see the temperature scale of this temperature or this energy and temperature. So we do have the temperature scale. Temperature scale. In order to define any temperature scale, two fixed points are very important. One, the lower fixed point and the upper fixed point. These 2 points are very important. That means the lower fixed point of this scale is the temperature of melting ice. The lower, because we do have the lower fixed point for degree Celsius and degree Fahrenheit and also for Kelvin. And the upper fixed point for degree Celsius and degree Fahrenheit and Kelvin. However, we are considering the lower fixed point of water and the higher fixed point of water. Let's say the lower fixed point of ice is 0 degrees Celsius. That means 0 degrees Celsius is lower fixed point. and 100 degrees Celsius is the upper fixed point. For what? For degrees Celsius. The distance between 0 degrees Celsius and 100 degrees Celsius, let's say, is called centigrade. Centigrade. The name centigrade scale meaning 100 step. 100 step. It means centigrade means it's 100 steps. Therefore, temperature and heating, under temperature and heating, where we have to calculate or prove the temperature scale. The Fahrenheit or the Fahrenheit freezing point of water is 32. Therefore, 32 degree Fahrenheit is the lower fixed point, and 212 degree Fahrenheit is the upper fixed point for degree Fahrenheit. The difference between the lower or the upper fixed point and the lower fixed point is about 180. The difference is 212 minus 32 is equals to 180. This means the difference between lower fixed point and the upper fixed point is divided into 100 equal interval. Each interval corresponds to 1 Fahrenheit. There corresponds to 1 Fahrenheit. Anyway, remember that 100 parts in centigrade is equivalent to 180 parts in Fahrenheit. In both Celsius and Fahrenheit scales, both positive and negative values of the temperature could be exist. That means in degree Fahrenheit and Celsius we can get both positive and negative values. But in case of Kelvin, we couldn't get negative values. That is, the only we get is 0 Kelvin. This 0 Kelvin is called absolute zero. 0 Kelvin is called absolute zero. Absolute zero. Its value has been measured to be about negative 273 approximately 16 degrees Celsius. That means the upper fixed point is 373.16 Kelvin, and the lower point is 0 Kelvin. The degree Celsius and the Kelvin scales differs about 273. The difference between degree Celsius and Kelvin is about 273. Therefore, let's see the interval. We say that the lower fixed point of the degree Celsius 0, and for degree Fahrenheit is 32, and we have to remember that the interval of this scale is the same as for the Celsius. Now let's see the scale conversion. The scale conversion of the degree Celsius and degree Fahrenheit and Kelvin. The ratio of, let's take the ratio for degree centigrade to degree Fahrenheit is 100 over 180, because the difference between the lower fixed point and the upper fixed point of degree Celsius is 100, and this is 212 minus 32 is 180. So we will get what? 5 over 9. And also the ratio for degree Fahrenheit to degree Celsius is 180 over 100, which is 9 over 5. Therefore, then 32 degree Fahrenheit equals 0 degree Celsius. So simply we can add this degree Celsius and the degree Fahrenheit, then the final degree Fahrenheit is 9 over 5 degree Celsius plus 32. This is to convert the degree Fahrenheit or degree Celsius to degree Fahrenheit. Our equation is this one. And degree Celsius is equals to 5 over 9 into degree Fahrenheit minus 32. And Kelvin is degree Celsius plus 273. And also Kelvin is 5 over 9 into Fahrenheit minus 32 plus 273. This is to change Fahrenheit into Kelvin. These are some basic units of what? The units of degree Fahrenheit and degree Celsius. So in general, as a temperature raises, a heat energy of the particles converted to kinetic energy. When it gets heat energy, the particles get heat energy, means their kinetic energy is increasing. But if two bodies are in thermal equilibrium, they will also be at the same temperature. Thermal equilibrium means they are at the same temperature. So we do have 3 laws of thermodynamics in this case. The first law of thermodynamics states that change in internal energy is the sum of the heat energy added to the system and the work done on the system. Therefore, they'll say change in Q is equals to change in U is equals to change in U is equals to change in Q plus change in W, when this is the internal energy in joule, and this one is heat energy added to the system also in joule, and this is the work done on system, also the unit is joule. Also the other is zeros law of thermodynamics. The zeros laws of thermodynamics states that if object A and B are individually in thermal equilibrium with object C, that means A is equal with C, B is equal with C in temperature, so that A is also equal to B. This is the law of zeros law. Shortly, we can say that it states that the object A and B are individually in thermal equilibrium with another object of C. Object A and object B are also in thermal equilibrium with each other. This is zeros law of thermodynamics. Second law of thermodynamics tells us that energy or heat cannot be flow from low temperature to high temperature. Simply, the law states that it concerns with the direction of the direction of heat flow. It talks about heat flow. the direction of heat flow between two bodies. It states that heat generally cannot flow spontaneously from a material at lower temperature to the material high temperature. So that ስንት ህጎች አሉን ማለት ነው? ሶስት ህጎች አሉን የቴርሞዳይናሚክስ። አንደኛው first law thermodynamics, second law thermodynamics, and zeroth law of thermodynamics. So when body gets temperature, that body will be expanded. Let's see about the linear expansion, area expansion, and volume expansion. Therefore, linear expansion, area expansion, and volume expansion. እነዚህን ካልኩሌት እናደርጋቸዋለን። Most materials expand or increase in size when heated and contracted when the heat is decreased or when they cooled. However, the amount of expansion or contraction varies from material to material. ከአንዱ ወደ አንዱ expansion እና contraction ይለያያል. In general, when change in L is equals to L naught alpha change in temperature. This is for linear expansion. Linear expansion በምን ያህል ነው የሚለወጠው ማለት ነው? LF minus L naught change in L means LF minus L naught alpha change in temperature. When alpha is coefficient of linear expansion. This is change in temperature. This is the original length. Let's say this is our original length. Let's say this is L naught. But when you are heating up, that length will be increased by LF. So to get the change in L, there is a change in L here. Change in L is LF minus L naught. Change in LF. Therefore, LF is equals to take this one to the right side and L naught plus L naught alpha change in temperature. LF is equals to L naught into 1 plus alpha change in temperature. This is our general formula to calculate the increased in length of the linear expansion. This increase in length of area expansion, linear expansion. Now let's calculate the area expansion. Now we know that area is length times length. Therefore, L square. AF area of final length area is equals to LF square. Area naught is equals to L naught square. Mind you. Therefore, change in A is equals to A naught beta times, or let's put this as AF to calculate AF. First of all, let me prove for area. Therefore, let me say that proof area expansion. Let's prove area expansion. AF is equals to LF square, but I do have LF, which is equals to L naught plus L naught alpha change in temperature. Therefore, LF means AF is equals to square root of what? Or the square of L naught plus L naught alpha change in temperature the whole square. I substitute instead of LF this one. Then L naught plus L naught plus L naught alpha change in temperature times L naught plus L naught alpha change in temperature. L naught times L naught square, alpha square change in temperature square plus this times this L naught alpha change in temperature, this times this is L square, sorry. Then L naught times this L naught square alpha change in temperature plus L naught times L naught square. Therefore L naught square plus this one is 2 L naught square alpha change in temperature plus L naught square alpha square change in temperature square. Then I can write this L naught into 1 plus 2 alpha change in temperature plus alpha square change in temperature square. Therefore this is equal to what? AF is equals to L naught square into 1 plus 2 alpha change in temperature plus alpha square change in T square. When we compare this one with this one is smaller, therefore this one can be vanished. What is left? AF is equals to L naught square into 1 plus 2 alpha change in temperature. Now L naught square means equal to A naught. Therefore increasing in AF is equals to A naught plus 2 times alpha change in temperature, when 2 times alpha is equal to beta. Therefore our final AF is equals to A naught into 1 plus beta times change in temperature, when this one is coefficient of area expansion. Now we calculated what? Area expansion. Now let's prove for volume expansion. Okay, we have still LF, or LF is equals to L naught plus alpha change in temperature. This here is L naught is equal. Therefore therefore here is LF is equals to L naught plus L naught alpha change in temperature. Now volume is equals to, let's say VF is LF the power of 3. Why? Volume is length times width times height. Let's say L, therefore we can multiply them, L the power of 3. But I do have what? LF, which is L naught plus L naught alpha change in temperature. Now let me multiply it 3 times. Let's multiply 3 times. When we multiply 3 times, we can find the volume expansion. Therefore this one L naught alpha, first of all let me find the square, which means L naught plus L naught alpha change in temperature. This times is L naught square alpha square change in T square plus L times L naught square alpha change in temperature. This is L naught square alpha change in temperature plus L naught square. This is equal to L naught square plus L naught 2 times L naught square alpha change in temperature plus L naught square alpha change in temperature. And this one is also multiplied by L naught plus L naught alpha change in temperature. This can be written this form. This times this number. This is L naught square plus 2 L naught square alpha change in temperature, L naught square alpha change in temperature plus this one L naught alpha change in temperature into L naught square plus 2 L naught square alpha change in temperature plus L naught square alpha change in temperature. Now let's finish this one. Let's finish this one. Okay. When we finish this one, L naught times L naught square is L naught cube. L naught cube plus L naught times this 2 L naught cube alpha change in temperature plus L naught cube alpha change in temperature. Change in temperature. Okay. Let's say this is star 1. Let me put this as star 1. This one is, I think, this square. Yeah, there is a square. Therefore L naught plus 2 L naught cube alpha change in temperature L naught cube alpha square and change in T square. This is star 1 because here is a square. There is a square here. And 2 this one, which means L naught alpha change in temperature into L naught square plus 2 L naught square alpha change in temperature plus L naught square alpha square change in temperature square. This one. Okay, this one is equal to L naught cube alpha change in temperature. L naught cube alpha change in temperature plus this one is 2 L naught square, this is cube, sorry, alpha square change in temperature square plus this one is L naught cube alpha cube change in temperature cube. Okay, this one is let's say star 2. Now let's add them. And this one is star 2 and star 1. L naught, when we add them, L naught cube plus 2 L naught cube alpha change in temperature plus L naught cube alpha square change in temperature plus this one L naught cube alpha change in temperature plus 2 times L naught cube alpha square change in temperature square plus L naught cube alpha cube change in temperature cube. Now L naught cube is constant, therefore 1 plus 2 this is L naught is alpha change in temperature plus alpha square change in temperature, alpha square change in temperature. Okay, this one is when we add them, star 1 is equal to this is yes, okay, then plus, here is plus alpha change in temperature plus 2 alpha square change in temperature square plus alpha cube change in temperature cube. Now we can add this and this one. This gives us 1 plus 3 alpha change in temperature plus alpha square. This is a square, yeah, square. This one is also a square, and this plus this gives us 3 alpha square change in temperature square plus alpha cube change in temperature cube. Now when we consider this number with this one, they are very small. This one is very small, therefore they will be vanish. Then what is left? V final is equals to L naught cube into this one 1 plus 3 alpha change in temperature. This is equal to V naught into 1 plus 3 alpha change in temperature, when gamma is 3 times alpha. Therefore, V final is V naught into 1 plus gamma change in temperature. This is our general equation to find the increase in volume. The increase in volume. Okay. On the other hand, let's see the now volume expansion and area expansion. We get the formulas how to calculate. So generally we can put them as general. Let me write them. The general formula. Okay, the general formula. Therefore, the general formula will be LF is equals to L naught into plus alpha change in temperature. Area final is A naught into 1 plus beta change in temperature, and change in volume is equals to V naught 1 plus gamma times change in temperature. The other is bimetallic strip. Bimetallic strip. What is bimetallic strip means? A strip made up of two different metals. A strip made up of two different metals bonded together along their lengths, and when they heated up, the one with low coefficient linear expansion, coefficient of linear expansion will expand than the other. Let's say if we have iron and brass and iron. Let's say here is iron and brass. The coefficient of brass is less than that of the iron. Therefore, since it has low coefficient of linear expansion, when you heat it up, this metal will be the length of the brass will be increased than the iron. Then it will bend toward the iron. It looks like this. This is iron, this is brass. Why? The coefficient of linear expansion of the brass is less than that of the iron. This is known as the